Next we come to a protocol which is in a way the mirror image of superdense coding, and this is called teleportation. Yeah, the setting is also in a way the mirror image of superdense coding. Imagine the following situation. Again, Alice and Bob. And this time, Alice has a qubit in some quantum state. And it's an arbitrary superposition state. Can be any state. Doesn't have to be a basis state. And Alice wants to transmit this quantum state to Bob. Yeah, so in her lab, she has a qubit in this particular state, and she wants to convey this quantum state to Bob's lab, and Bob is far away. She cannot physically send the qubit, however. All that she has at her disposal is a classical channel. So here the constraint is that Alice may only send classical bits to Bob. And only a finite number of classical bits. So this is another task which may look impossible at first. If you remember that the pure state of a qubit can be visualized as a point on the surface of the Bloch sphere, then a pure state is specified by the coordinates on this Bloch sphere. So if you want, in an entirely classical way, if you want to send to somebody else complete information about the pure state, you have to send these coordinates. And if you want to do that with infinite precision, then you have to send sort of an infinite number of digits for these coordinates. So you need an infinite number of classical bits to specify precisely the one point on the surface of the sphere. Here, however, Alice may only send a finite number of classical bits and still wants to transmit the qubit state perfectly, not in some approximation. And there's a protocol, this protocol called teleportation, which does that, which achieves that by sending only 2 classical bits. Once again, there is a trick. There is the trick that Alice and Bob previously shared a Bell pair. Once again in this particular Bell state beta 00. So we have at the start of the protocol, we have now 2 qubits on Alice's side. We have the qubit in this state psi that Alice wants to send to Bob, and in addition she has her member of the Bell pair. So at first we have this state psi 0 of all 3 qubits involved. So that's the qubit in the state psi, and that's the 2 members of the Bell pair, of which one is on Alice's side and the other one is already on Bob's side. This psi 0 is at first a product state of psi with the Bell pair. And let's say that the state psi is an arbitrary superposition of the standard basis states with amplitudes alpha and beta. So let's say this is alpha 0 plus beta 1. And the belt state, that's once again this superposition of 0, 0 plus 1, 1 over square root of 2. Let me forget once again the 1 over square root of 2's and write this as a proportionality. And let me multiply out the bracket here, at least in part. And let me write that as alpha 0 tensor 0, 0 plus 1, 1 plus beta 1 tensor 0, 0 plus 1, 1. Then the first thing that Alice does is to couple the qubit in the state psi to her member of the bell pair with a C0 gate. So Alice applies a C0. And this gives the state psi 1. Let's look now at this psi 1 up to proportionality. Let's start with the expression in the previous line on the right hand side and consider the various possibilities. If the control qubit, so that's the upper qubit, if that is in the basis state 0, then nothing happens and the target qubit or the basis state of the target qubit remains unchanged. So then actually we have the same state as before. So that's tensor 0, 0 plus 1, 1. But if the control qubit is in the basis state 1, then the standard basis state of the target qubit flips. And the target qubit, that's the first qubit in the bell pair. So instead of 0, 0, we get 1, 0, and 1, 1 becomes 0, 1. Yeah, so we have a flip in the first, for the first member of the bell pair. In the next step, Alice sends the first qubit through a Hadamard gate. And this gives a state psi 2. Now, what does the Hadamard gate do to the basis state 0 that we have here of the first qubit? The Hadamard gate transforms a basis state 0 to a plus state. Plus state is a superposition 0 plus 1. We forget the square root of 2. So this becomes 0 plus 1. The rest remains unchanged, so we have 0, 0 plus 1, 1. And then comes the second contribution with the basis state 1, and that is transformed to a minus state, which is 0 minus 1. And then again, tensor the rest. And now we group these various contributions in a different way. We look at all terms that have basis state 0 for the first qubit and for the first member of the bell pair. So that's the case here. So when we multiply out all the brackets, then we get here 0 and here a 0. And the same happens again here. And then we have a 0 for the first qubit and also a 0 for the first member of the bell pair. And we factor out then a 0, 0. Yeah, so here writing it in this way, the first 0 refers to the first qubit in the circuit, yeah, which was originally in the state psi. The next entry refers to Alice's member of the Bell pair. And then we have alpha. So this alpha here. And this basis state 0 here. So alpha 0. And then it happened again here, we said. Beat 0, 0. And then we have in front a beta. So we have plus beta. And the Bob's member of the Bell pair is in the basis state 1. So we have beta 1. Then we look at all terms where we have the first qubit in the basis state 0 and Alice's member of the Bell pair in the basis state 1. Let's see where that happens. It happens here. We have 0, 1, 1. Yeah, so the remaining qubit, that's Bob's member of the Bell pair, is then in the basis state 1. And we have in front an amplitude alpha. So we have alpha 1. And then it also happens here. We have 0, 1, 0. So there, Bob's qubit is in the basis state 0. And we have in front an amplitude beta. Then, next, we look at 1, 0, and finally at 1, 1. So where do we have the combination 1, 0? It happens here. We have 1, 0, 1. Yeah, so indeed Bob is then in the basis, or Bob's qubit is in the basis state 1 with an amplitude beta, and here we have a relative minus sign. So with a minus beta. And it also happens here. We have 1, 0, 0. So Bob's qubit is in the basis state 0 with amplitude alpha. Finally, the combination 1, 1. When does that occur? So we have it here. 1, 1, 1 with amplitude alpha. So Bob's qubit is in 1 with amplitude alpha. And it also occurs here. We have 1, 1, 0. So Bob's qubit is in 0 with amplitude minus beta. There's a relative minus sign. Okay, so these are the 4 possible combinations for Alice's qubits. And we grouped by these 4 possible combinations. In the next step, Alice performs measurements on her qubits in the standard basis. And the outcomes of these measurements, these are the 2 classical bits that Alice physically sends to Bob. Bob receives these classical bits and uses them for operations on his side. You can already see, looking at the state psi 2, that there are 4 cases corresponding to the 4 possible measurement outcomes of these 2 measurements. If Alice measures, or if the outcomes of both measurements of Alice are 0, then the state psi 2 is projected onto the eigenspace corresponding to this to these measurement outcomes. So the measurements will change the state, and the state change is a projection onto the eigenspace corresponding, associated with the outcome that was obtained. So if Alice measures 0, 0, then the state psi2 is projected onto the associated eigenspace. If you look at the 4 contributions to the sum, to the superposition here in psi2, there's only one term which lies in this eigenspace, and that's the first one. It's the one 0, 0, 0. These are all tensor products here. I forgot to write them explicitly, but of course these are all tensor products. And of these 4 tensor products, only one lies in the eigenspace associated with the measurement outcome 0, 0, and that's the first one. So after this projection, you know that Bob's qubit must then be in this superposition state alpha 0 plus beta 1. After the projection, only this first tensor product survives, and from this you immediately read off that Bob's qubit is in this superposition state. And likewise for all the other cases, if Alice measures 0, 1, then Bob's qubit is in this superposition state here, alpha 1 plus beta 0, and so on. So from this expression, from this superposition, you can immediately read off the state of Bob's qubit depending on the outcome of Alice's measurements. Now you see that if the measurement outcome was 0, 0, then Bob's qubit is already in the desired state. It's in the superposition state alpha 0 plus beta 1, which was precisely the state psi that Alice wanted to send to Bob. So Bob doesn't have to do anything. Bob's qubit is automatically in the desired state. If the measurement outcome was 0, 1, then it's not the desired state. We would like alpha 0 plus beta 1, but it is in the state alpha 1 plus beta 0. What does Bob have to do in order to transform this state into the desired state? He has to flip all the basis states. He has to turn the 1 into a 0 and the 0 into a 1. So he has to apply a Pauli X. That's precisely what Pauli X does. It flips the basis states. What if the measurement outcome was 1, 0? Then again, it's not quite the state that Alice wanted to transmit. It's alpha 0 minus beta 1 rather than alpha 0 plus beta 1. What does Bob have to do in order to transform this state into the desired state? He has to flip the sign in front of the basis state 1. That's achieved with the Pauli Z operator. The Pauli Z leaves the sign of, doesn't do anything with the basis state 0, and it flips the sign in front of the basis state 1. And then Bob possesses the state psi. And finally, the last possibility, if the measurement outcome was 1, 1, then Bob's qubit is in this state here. And that's now wrong in 2 ways. There is a minus sign here in front of the basis state 0, and also the basis states are wrong, right? So instead of alpha 1, Bob would like to have alpha 0, and instead of minus beta 0, Bob would like to have plus beta 1. Yeah, so Bob would like to change once again the relative sign of these two basis states, and in addition flip them. So Bob has to apply a Pauli X and a Pauli Z in order to get the desired state psi, yeah, from Alice. Now all of this is achieved by means of the following simple circuit on Bob's side. Bob uses the second of the classical bits in order to control a Pauli X on his member on the bell pair. And he uses the first classical bit received from Alice in order to control a Pauli Z, once again on his member of the bell pair. You can go through all these four possibilities that we just discussed and verify that the Pauli X and the Pauli Z operations correct precisely the deviations from the desired state that we identified. Yeah? So maybe we pick the last case as an example. Yeah. So Bob uses the second classical bit, which has the value 1 in this case, to control Pauli X. So Pauli X is applied. This flips the basis states. So this turns minus beta 0 plus alpha 1 into alpha 0 minus beta 1. And then Bob applies a Pauli Z, and that changes the sign in front of the basis state 1, and this turns this into alpha 0, 0 plus beta 1. And that's the state psi that Alice wanted to send. And it works for all the four cases that we have identified. So in all four cases, after Bob's operations, his member of the bell pair, his qubit, is in the state psi. So effectively, the circuit has achieved precisely what was intended. Bob's qubit at the end of this protocol is in the state psi that was previously on Alice's side. Let me quickly run through the protocol once again on the slide to summarize the various steps. So Alice couples the qubit whose state psi she wants to send to Bob to her member of the bell pair with a C0 gate. Then applies a Hadamard gate just to the first qubit. Then performs measurements on her two qubits in the standard basis and sends the results of these measurements to Bob through the classical channel. And these are two classical bits. Bob uses these classical bits to control operations on his side, Pauli X and Pauli Z. And at the end of these operations, his qubit is in the state psi. It's important to note that neither Alice nor Bob know the state psi. So they never measured the state psi. The state psi has been teleported from Alice to Bob, but they don't know what that state is. On Alice's side, the qubit may be the the end product of some protocol, of some experiment, and Alice doesn't know and doesn't have to know what the state psi is. And at the end of the protocol, the state psi ends up on Bob's side, so Bob's qubit is now in that state psi. And also Bob doesn't know and doesn't have to know that state psi. He knows it's in the same state that was previously on Alice's side, but what that state is, what the amplitudes alpha and beta are, that is not specified and that's not known to Alice and Bob. And another important remark is that at the end of the protocol, Alice's qubit is no longer in the state psi. Alice used the qubit in the state psi. She coupled that to her member of the Bell pair, and then at the end she performed measurements. And after the measurement, of course, the qubits are all in basis states, because the measurement was in the standard basis. So they are all in standard basis states. They're no longer in superposition states. So the state psi has been destroyed on Alice's side. It's gone. It vanished and it reappeared on Bob's side. And that's the way it has to be, because if the state psi was still on Alice's side, then effectively this protocol would have copied the state, and that would have been in violation of the no cloning theorem. You cannot copy a quantum state. So in order for it to appear on Bob's side, it has to be destroyed on Alice's side. And a final remark, and that also applies to the superdense coding protocol that we saw earlier. The Bell pair has also been destroyed. Yeah, so after the various operations, and in particular after the measurement on Alice's side, the entanglement is destroyed, and the two qubits they are no longer entangled. They are no longer in a Bell state. And the same also happened in the superdense coding protocol. So in this sense, the Bell pairs are like a resource that you can use only once. You consume a Bell pair and then it's gone. You can't reuse it to, say, do this protocol a second time. It's something that you consume, and then it's burnt and then it's gone.